Good afternoon, everyone. Welcome to the fall Colloquium series in optical sciences. I'm going to be your host for most of this semester. I'm Amit Ashok. I'm a faculty in image science. And we have a great lineup of speakers this semester. And before I get into the particulars, I would especially like to extend a warm welcome to our incoming class of students this fall. I'm sure you'll find these seminar series really, exciting and entertaining, and hopefully learn a great deal from the different distinguished speakers. So with that, I'll kick off the seminar series. Our first speaker is Professor Euan McLeod. He just joins us this fall semester. He's assistant professor here. He had previously had a tenure as a postdoc in electrical engineering and bioengineering in UCLA. And before that, he had a postdoc tenure at Caltech in applied physics. He holds a PhD degree from Princeton University and a Bachelor's of Science degree from Caltech. Euan's interests lie at the intersection of optics, nanoscience, and soft biomaterial science, so it's quite a multidisciplinary area. He's published more than 20 peer-reviewed papers on these topics, and his most recent work has been in a mixture of experiments and simulations with the goal of improving the sensitivity of lens-free holographic microscopy for imaging virus-sized and smaller particles. So with that introduction, I'll hand it over to Euan. He'll be talking to us about soft nanophotonic systems today. Thank you.
Thank you very much for the introduction, and it's great to be here. I'm having a great first few weeks, and I'm settling in. I'm meeting with students, working with students. We're getting equipment, getting my lab set up, meeting everyone. I've had a warm welcome from everyone. I'm very happy to be here and appreciate the reception I've received. So if anyone wants to stop by and talk to me either more about what I'm going to talk about today or just in general, I'm in room 623, so feel free to come by. And before I get into the kind of meat of my talk, which is this main research project, I'd like to talk a little bit about my general overarching themes, which Amit mentioned a little bit. And that's the idea of soft nanophotonic systems. And so this is really the intersection of three areas. It's soft material, nanophotonics, and then systems of many components. So soft material include things such as liquids, polymers, biological materials, surface forces, so things such as electrostatic forces, van der Waals forces, these types of interactions. Biochemical interactions, which could be looking at things such as how antibodies bind to their antigens, and then material transport, which could be things such as diffusion. Nanophotonics, you're probably all much more familiar with, so this includes things such as resolution beyond the diffraction limit, beyond lambda/2, optical sensing of nanoscale objects, which is more of a signal-to-noise problem, but often is closely tied to resolution. Optical nanopatterning, which is the ability to write very small structures on surfaces with feature sizes smaller than, hopefully below this diffraction limit, looking at the optical properties of subwavelength structures. And then the systems aspect is the coordinated interaction of many components. So this could be things such as colloidal particles interacting in solution. It could be looking at how things self-assemble. And so the self-assembly often ties in with surface forces. That if you have small particles or objects coming together and you want them to come together in some organized fashion, how are they going to do that? Directed assembly is kind of a mixture of self-assembly, but also with a little bit more user input. And the idea is you can get a more specific structure, although you might sacrifice a little bit in terms of throughput. And then stochastic interactions, which look at the probabilistic interactions of these types of components and have to do with things such as kinetics and thermodynamics, these sorts of areas. So soft nanophotonic systems have already had impact in a number of different areas. I want to choose a few examples that are from my previous work, either as a PhD student or as a postdoc. And one of the main areas of impact that I particularly have worked in is fabrication. And so this is one example where what we were trying to do, this was a nanopatterning example, where we were trying to create very small features on a surface. So you can imagine this sort of being like lithography, where you're trying to write a specific pattern onto a surface. And you want to get this pattern as small as possible. And so what we did was we actually used a microsphere, so this could either be polymer or it could be silica, as a near-field objective. So this gap here was smaller than about 100 nanometers. This microsphere is then held within the near field of whatever you're trying to pattern. And what we're doing is we're holding this microsphere here with an optical trap or an optical tweezer. In this case, we're using a Bessel beam optical trap. And what we can do is we can then drag these particles around with this Bessel beam optical trap. So this is looking at an array of 4 particles. And you can come in with a second laser that's actually going to be doing the materials processing and creating small features that are kind of directly written in with a laser into the substrate. So what we're able to do with this is we're able to create feature sizes smaller than about 100 nanometers, and the wavelength that we're using is about 365. This provides a little bit better than lambda over 3 in terms of resolution. This is another example of some work I did. In this case, this is looking at another way of doing some nano patterning or some lithography on a surface. In this case, we're trying to pattern this polymer nanofilm. And this polymer nanofilm is heated up so that it becomes a liquid. So it's a very viscous, soft liquid. There's a strong temperature gradient that we impose across this. So a cold plate on the top, a hot plate on the bottom. This leads to a destabilization or an instability in the polymer film. So rather than remaining flat, it spontaneously forms these ripples. And we can kind of seed where these ripples are going to be formed if we structure this top plate. And so this would be an example where we're creating something like a microlens array. So this is an array of kind of small bumps on a surface that could be used, for example, to focus light. This is another example from some previous work where we're looking at creating an adaptive lens here. So this is a lens. It's the cylindrical chamber. It's filled with a liquid polymer, silicone oil in this case. And we have a piezoelectric around the end, which is sending vibrations through this liquid. These vibrations are actually causing lensing effects through the liquid, and then you can combine this with other lensing equipment, other imaging equipment, in order to image specimens. So this is an example of combining it with a 2-photon microscope, where we're imaging a Drosophila embryo, and you can get different sorts of images when you use this high-speed lens compared to a normal lens. So I'm not going to go into too much detail about these. I just wanted to give you kind of a flavor of what I mean by these soft nanophotonic systems. Most of what I'm going to talk about today is being able to improve the sensitivity so that we can detect very small particles. In this case, we're going to be detecting nanoscale particles, but across a field of view that's millimeters by millimeters. So there's a very large difference in scale between what we're sensing and the number of particles or the area with which we can sense them. And then, of course, there are other areas. These are areas that I haven't in particular worked in, but things such as energy. So dye-sensitized solar cells is another example where the nanoscale interactions between the soft material, in this case the liquid dye, and the hard material and the light provides energy. Other examples are materials physics, things such as colloidal crystals, studying these types of interactions. So now this is the main area. So this is really the main part of my talk, and it's looking at nanolenses for on-chip holographic imaging of nanoparticles and viruses. And so before I get into the details, I want to, of course, acknowledge the previous group. So I was previously working with Aydan Özkan at UCLA, and so this is him in the center. And this is a very large group of people who are here. It's a little bit deceiving how large it is, because he actually has a grant from HHMI in order to fund an undergraduate research training. So more than half of these, I think about 35 of the people here are undergrads, and so there was a very large number of other undergraduates doing research in our group. So if there are any undergraduates here who are interested in doing research, come talk to me, and I'd be very supportive of that, and I think it worked out quite well. But then, of course, I'd also like to acknowledge all the other postdocs and graduate students who are also working in this group and kind of helping this effort. So again here, the main goal of what I'm going to talk about today is to develop a label-free, rapid, wide field of view, portable, and low-cost nanoparticle and virus imaging technique. And so the reason why we want to be able to image and detect these nanoparticles and viruses are for a number of different applications. They include things such as biomedical applications, where you can do things such as perform viral load count. And one example of this is in looking at HIV patients. You want to count the number of copies of HIV in someone's bloodstream. Counting exosomes. So exosomes are small little particles that bud off of cells. You can imagine like a little bit of the cell membrane buds off, and this can be useful for evaluating the progression of cancer, for example. Tracking foreign substances. So if you introduce some sort of imaging contrast agents into the blood, you might want to track those. There are also environmental applications if you want to monitor the amount of nanomaterials that's either in the air or in the water. And then also nanomaterials engineering. So if somebody is trying to synthesize or fabricate a specific type of material, for example, say carbon nanotubes, they might want to know how many of these am I making? Am I making them in the correct size? Am I making them in the correct shape? These types of questions. So one question, so if you go back here, you'll notice that one aspect of this is that we're interested in portable and low-cost approaches here. And so one question is, why do we care about portable and low-cost? And so one reason is that if we look at those biomedical applications, there's an advantage of being able to move diagnoses from the laboratory, which is kind of the typical framework, into the field. So this was taken from a couple years ago. This is an example from one of these articles on the Ebola outbreak last year. And in this case, what happens is you're treating patients and you're taking blood samples in an environment like this, but to actually make some sort of diagnosis, the kind of traditional paradigm is that you take these samples, you send them to the lab, they perform some analysis, and then they send the results back. But of course, this can be expensive and slow and time-consuming, and so if you can do these sorts of diagnoses on very small, portable pieces of equipment, that can speed things up if you can actually do the diagnosis in the field. So in a lot of cases, this will be interfacing something with smartphones. In other cases, it's small, portable pieces of equipment that could plug into, say, a laptop or a tablet. And the idea is that this can speed up diagnosis and reduce cost. And then the other advantage is that you can enable telemedicine. And so if you have these sorts of platforms where they can track the location where these diagnoses are being made, you can very easily kind of bring up these sort of heat maps of where things are happening. So this is one example looking at environmental monitoring from our group, where they were doing environmental monitoring using a smartphone, and this was looking at mercury contamination along the beach in Los Angeles, and they could collect samples from different areas and then build up this sort of heat map. But you can imagine this being kind of done over a larger scale where you have information from across the world and you can track epidemics and these sorts of things. So I'm going to show you how we can achieve this goal, this label-free, rapid, wide field of view, portable, and low-cost nanoparticle and virus imaging technique via a combination of microscopy and sample preparation. So the microscopy approach is going to be this lens-free holographic on-chip microscopy, and so I'm going to spend a few slides talking about that. And then the sample preparation approach is the self-assembled nanolenses, which are going to boost our sensitivity and make it so that we can see these really small particles that are at the virus scale that we're trying to detect. And then I'm going to close with some extensions we've done on specificity, portability, and particle sizing. So this is our imaging approach. So before I want to get into that, I'm going to contrast it with conventional optical microscopy. So this is one of the earliest microscopes. This is from Robert Hooke. And if you compare this type of microscope to a modern-day microscope, you'll notice that there are many of the same components there. You still have a light source, you have a condenser lens, you have your sample, you have an objective, you have an eyepiece. And if you look at a modern-day microscope, you have the same sort of elements. And because of the fundamental way in which these microscopes are kind of built and designed, you end up with a number of trade-offs. And these trade-offs include sensitivity, resolution, field of view, portability, and equipment cost. So what I mean is, let's say we're trying to detect the smallest possible particles. Typically what you're going to do is you're going to start at a 4x microscope objective and then work your way up in terms of magnification. So as you work your way up, you're going to improve your sensitivity, you're going to improve your resolution, but you're going to sacrifice field of view. And so that's what I'm illustrating here. So you're going to get smaller and smaller field of view. Also, if you want to detect the smallest possible particles, you typically need fairly large, bulky laboratory equipment that can be fairly expensive. So I'm going to show how we can attain all these qualities using on-chip microscopy. So this is the on-chip microscopy platform. It's quite simple. All there really is a light source, and this light source can be as simple as an LED coupled to an optical fiber. There's then your transmissive sample, which is what you're trying to image, and then you have a sensor chip. So the sensor chip could be a CMOS or a CCD sensor chip. In this case, what we're using is a sensor chip that's about 4 millimeters by 5 millimeters. And so one thing you'll notice is that this has a very large field of view. And so if you compare this field of view to, say, a typical 40x microscope field of view, you'll see that our field of view is hundreds of times larger. Some other things that you'll notice are that this is fairly simple and portable. Everything here is fairly small, so this dimension is about centimeters, so you can have a very small, compact microscope that you can carry with you and use in the field. It's also very inexpensive, so the most expensive component might be this image sensor chip, but because these are mass-produced for cell phones, they can be a few dollars or a few tens of dollars. So you get these three benefits, but of course you might have some questions. Since there aren't any lenses in this system, how do we actually form an image? How do we actually see something that's in focus on our sample? What sort of resolution can we achieve? And then what sort of sensitivity can we achieve? So the imaging that we perform is not the typical imaging. It's actually inline holography. And this inline holography you can think of as an interference effect. And this interference effect is the interference between a direct ray that's passing straight through the sample and then a ray that gets scattered off of the object. And so the reason why we're able to actually record an interference pattern is that we have a partially coherent light source. So we have enough coherence in order to see these interference effects. And in order to ensure this coherence, we have to have spatial coherence. So we have a pinhole here, but this pinhole is relatively large. It's maybe a few hundred microns, so that's a little bit larger than maybe the normal pinhole someone might use. And then we also have a spectrally limited source to give us temporal coherence. And so our source is about 3 nanometers in bandwidth. So what this does is it provides us enough coherence to see these interference effects, but it's not the same level of coherence as you might get from a laser. And the advantage of this is we can actually reduce the type of speckle artifacts that you might normally see in coherent imaging with a laser. So as I said, we're recording this interference pattern. This interference pattern you can think of as an interference between a reference wave and a signal wave, and then kind of the typical holography kind of framework. And what we're trying to recover here is this signal, and we can recover the signal by this interference pattern. So in our case, one thing that you'll notice is that our hologram is its resolution that we record is initially limited by pixel size. And in order to get the smallest possible pixels, we typically turn to color image sensors because they tend to have smaller pixels. In this case, the smallest we can easily acquire is about 1.12 microns in size. And when you have a color image sensor, it follows this typical Bayer sort of pattern so that the pixels aren't all sensitive to each color, but you'll have a pixel sensitive to green, a pixel sensitive to red. This is a pixel sensitive to blue. And so since we're using a spectrally limited light source, in this case it's about 480 nanometers, so it responds well to green and to blue. We get fairly good response on the green and blue, but the red pixels appear dark. And so that's why you see this checkerboard type effect here. But buried beneath this checkerboard effect, you can probably begin to see some signatures of these concentric rings, and those are these holograms that we're recording. So initially, this hologram resolution is limited by the pixel size. So in a normal imaging approach, your resolution is limited by the numerical aperture of your objective. Here, we don't have a lens, so we're not limited by the numerical aperture of the objective, but we're limited by the pixel size. So we want to do a little bit better than this. So we want to be able to get better than that 1.12 micron half-pitch resolution. And so one of the approaches we use is pixel super resolution. So this is the same sort of thing that you might see on movies or TV, that if you have an object that's pixelated moving in front of, say, a security camera, it could be a person's face, it could be a license plate on a car. If you have multiple low-resolution images that are shifting across this field of view, you can synthesize a high-resolution image from these multiple low-resolution images. So we're going to do the same sort of thing. We're only going to use the green pixels on our sensor. We're going to take whatever object we want. You could imagine sweeping that back and forth across the image sensor. And so this would be that same sort of thing looking from the side. You can sweep your object, and in that case, your hologram is going to sweep with the object. It's a little bit more convenient to sweep the light source because the tolerances we need aren't as high, but you get the same sort of effect. You can imagine this shadow sweeping back and forth across the CCD sensor as we sweep the light source. So what we can do is we can go from these low-resolution pixelated holograms to this high-resolution hologram. And in this case, we can get resolution down to about 225 nanometers half-pitch using this approach. So this is essentially very close to diffraction limited, very close to that lambda over 2 resolution in terms of half-pitch. So then the final step is how do we go from these holograms to actually what the object looks like? And this step we do computationally. So we'll take this hologram and then we'll computationally reconstruct what the objects would have looked like to be able to create this. And since we're doing this holographically based on this interference pattern, we can get 2 types of images. We can get an amplitude image, which is similar to a bright field microscope image, and then we can get a phase image, which is similar to maybe a phase contrast type image. And so we can do this computation. So in our case, we use the angular spectrum approach to do this type of reconstruction. So again, I want to stress that we have the combination of having very good resolution, very high resolution, at the same time as a very large field of view. So this is a typical Air Force resolution test target. Again, if you compare to a typical 40x microscope objective lens, your field of view of the 40x is very small compared to what we can see across this image sensor. But when we do our reconstruction, we can resolve all the way down to the end of this imaging target. So this is submicron resolution here in group 9, and we can get there. And we've fabricated our own kind of test gratings using focused ion beam. And this is kind of the limit. So this is approximately the limit. So this is a 225 nanometer grading line with, in this case, 372 nanometer resolution. So the best resolution in terms of numerical aperture is about 0.9 NA, and then the best resolution in terms of half pitch is about 225 nanometers on this grading. So I want to say, I think one thing I want to say is also my advisor is actually going to be coming here, my previous advisor, I don't know, is going to give me a talk. And recently we've done a little bit better than this using a slightly different approach, and I think he'll present a little bit more about that too. But actually combining this type of approach with a synthetic aperture approach, and we can get resolution that's about 1.4 NA using that type of approach. So numbers are a little bit better, but using what I've shown you so far, this is what we can do. So in addition to the main application that I'm working towards, which is this targeting and sensing and counting and imaging of viruses and nanoscale particles, there are a few other applications that are particularly well suited to this lens-free holographic imaging. One is identification of different types of cells. And so this is an example of looking at CD4 and CD8 cells. So these are 2 types of immune system response cells. And they're important in HIV diagnosis and tracking the efficacy of treatment, these sorts of things. The difficulty in counting these types of cells is in a normal microscope, they look essentially identical. Their only difference is in the types of membrane proteins that are expressed along the edge. And So in order to tell the difference, what we've used is we've used two different labels. One label is gold nanoparticles, and these are labeling these CD4 cells, and one label is silver nanoparticles, and these are labeling these CD8 cells. And when we label these cells with these two different types of particles, because of the plasmonic resonances, they exhibit different spectral properties. And so if you do this holographic imaging with different colors, you can tell the difference between these different types of particles. And what you can go from is unlabeled particles we essentially can't discern, to the two different types of particles we can now separate in terms of our computational reconstruction, and we can tell the difference between these different types of particles. So another type of example are applications that fall into the needle in a haystack type problem, where you might be looking for only one abnormal cell in a large amount of cells. So examples include pap smear imaging. Other examples include malaria imaging. So the idea is you have a large number of cells, and just because you look at one cell and it looks fine doesn't mean all the rest of the cells are fine. But on the other side, if you look at a large number of cells and you find just one that looks abnormal, that might be indicative of a larger problem. And so you want to make sure that if you're a pathologist screening for malaria or for a pap smear, you want to be able to screen a sufficiently large number of cells so that you can identify whether or not you really believe this person is at risk. And so the ability to have the high resolution to screen individual cells, but also the large field of view so that you can see a lot of cells at the same time is very helpful. So then the last area of category of applications which are pretty well suited to this lens-free holographic imaging is 3D imaging. So because we can do our focusing and our reconstruction computationally, we can capture one image and then we can refocus that at many different depths. And so the ability to refocus at many different depths gives us 3D image tracking. So this is an example of an experiment where we're looking at thousands of sperm in kind of a single volume, and so there's some sort of chamber volume, and we're tracking their trajectories. And so it turns out a few of the sperm have this sort of very nice helical trajectory that I'm showing here. A lot have a much more chaotic random trajectory. But with this approach, we can get very large statistics, and we can quantify how many different types of trajectories we can see. So one interesting result that came as a consequence of this is that you can imagine there are two types of helices. There's a right-handed helix and a left-handed helix. And in human sperm, it happens that the right-handed helices are preferred 9 times out of 10 to left-handed helices. And we don't know why, but it's an interesting sort of result. Yeah, everyone says that, but I don't know. So yeah, so that's the idea behind lens-free holographic on-chip microscopy. So we get the advantage of high resolution and large field of view, portability, very cheap, very cost-effective, these sorts of ideas. But there's still a sensitivity challenge. And the sensitivity challenge is that particles smaller than about 250 nanometers are lost within the background noise of the reconstructed images. So we want to be able to get down below this size. So typical viruses are in the size range of about 25 nanometers at the small side up to maybe 200, 300 nanometers at the large size, that sort of range. So if we can get down below this, we can start to get into the realm of viruses. And the way we're going to do this is we're going to use the self-assembly approach. This is a sample preparation approach. And we're going to take whatever particle we want to detect, and we're going to embed it in this nanolens. And so this nanolens is made of a liquid polymer. It's a polyethylene glycol. And we're essentially going to grow this nanolens up around the sphere, and this is going to give us our increased contrast, our increased sensitivity. So this is the method we're using. We take the particles we want to detect. We somehow attach them to a hydrophilic surface. And this can either be done passively, in which case you just kind of dump everything from your sample onto the surface, or you can have specific capture. And I'll show this maybe 10, 15 minutes later, how we can do this with specific capture. So the next step is we take the sample, we flip it upside down, we suspend it above a pool of liquid polyethylene glycol. And so in this case, this is heated up to 105 degrees. This isn't boiling, but it's hot enough that some of this polymer is going to evaporate. The reason why we're using polyethylene glycol, a couple reasons. It's non-toxic, so you don't have to worry about doing this in a fume hood, is one major reason. The other reason is since we're using a polymer, we can control the molecular weight, and this means we can kind of control the rate of evaporation at different temperatures. So we do this for a couple minutes, so we don't have to wait too long. And then what we do is we take our sample, and we're going to put it on our lens-free holographic imager. And initially, we're going to do this on the benchtop, but then in maybe about 10 or 15 minutes, I'll also show you a portable device where we kind of combine these two steps together. So I want to say that before we really used this vapor condensation approach, we looked at a couple other approaches. And these other approaches included a flow-based formation where we took the particles we wanted to detect. We put them on top of our sample. We then gently tilted this sample so that this droplet rolled away. And then as it rolled away, some of these particles stuck to the substrate, and then they also pinned little droplets of liquid around them, which are these nanolenses. And using this approach, we could get down to about 100 nanometers. And so we could use this to image individual viruses in this case. We were also collaborating with a French group who were using a slightly different approach. In this case, they were using a solvent evaporation approach. And so the idea is that over time, a solvent evaporates and you get left with a very small, thin film here that's kind of buried around these particles. And in their case, they were a little bit more interested in imaging on conventional microscopes. So this is but with very low numerical aperture. So you get the same sort of benefit. You get a very large field of view because we're using a low magnification objective here. But we now have much higher sensitivity than you would normally have. So in comparison to what I showed you before, there are a couple limitations with these two approaches. One is they're limited to detecting particles about 100 nanometers or larger. So we've gotten a little bit below that 250, but we want to be able to do even better. It's also somewhat limited in terms of particle surface chemistry, because you have to make sure your particles kind of behave well in whatever liquid solution you're using here. So the advantages of this vapor condensation approach is that we can detect smaller particles, and I'll show you those results. We have greater freedom in terms of the particle chemistry. So many applications that we're trying to target require extracting a single type of particle from a heterogeneous sample. So this could be identifying viruses and other nanoparticles in blood. And so you'll notice here that in this case we did an experiment where we spiked fluorescent beads into blood plasma. And if you look at this carefully, we're able to detect these fluorescent beads using our lens-free approach. But there's also a lot of other things that are, small protein molecules that are forming clusters and things that are around this 100 nanometer size scale. Also, if you're wanting environmental monitoring, you might want some sort of specificity and nanomaterials engineering as well. Also important in these cases are the hydrophobicity of the particles. So in this case, you might want some sort of specific capture to be able to target a specific, say, virus. In this case, many of these particles might be hydrophobic, so you wouldn't be able to suspend them in that buffer that I showed you before. And so you need to use some sort of other method in order to get them on the substrate. And then the last is that we're actually able to do a before and after comparison of exactly the same field of view so that we can get a very quantitative assessment of the enhancement due to these nanolenses. So this is a typical sort of experimental result. This is our full field of view. These things are just some tape spacers that we had on our sample here. On the next slide, I'm going to zoom into this region of interest. And so this would be a reconstruction after doing this vapor condensed nanolenses, and you can see all these different effects. So there are a few different things. You see there are large particles here. These rings that you see them are an artifact of the holography. They're twin image noise. So there are ways that we could remove these. In our case, we aren't too worried about it because we're actually most interested in these small particles. So each one of these small dots corresponds to a small particle, and we verified this using scanning electron microscopy. So we take the sample, we then look at it in SEM, and we can say, for example, this spot corresponds to a particle 117 nanometers in diameter. This is 62, this is 48, and then this one's 38. So we've gone from a limit of about 250 nanometers as our sensitivity limit down to about 38 nanometers. And then the other thing, as I said, is we can do a before and after comparison. So if you look at before, you can see there's still these two large particles here that we can use as kind of reference marks. But all these smaller features, all these smaller particles, you wouldn't be able to see without these nanolenses. So these nanolenses really are necessary. So what we can do is we can notice what I've showed you before, which I guess I should say here, is that these images are actually phase images. So each one of these peaks corresponds to the phase signal that we're receiving from this particle. What we can do is we can plot this phase signal as a function of the particle diameter that we measure using SEM, and we see that there's some sort of relationship. So as one might expect, larger particles provide larger signals. And in order to make sure we have a strong understanding of the physics behind this enhancement, we want to kind of develop some models for what we're seeing and make sure our models agree quantitatively with what we see experimentally. And so these models consist of two parts. There's a nanofluidic modeling component, which is looking at essentially, first of all, the shapes of these lenses. And you can imagine there are two families of lenses. There are isolated lenses, where this film really reaches a finite contact point on the substrate. So it's like a little droplet just only around the particles. And then there are continuous film lenses, where this film covers the whole surface, and then it slowly kind of builds up as a function of time. So we're going to look at these different types of shapes. We can then model the growth rate. So how quickly is this film or these lenses going to grow as a function of time? What we're then going to do is going to send the results essentially from this nanofluidic modeling into optical modeling. We're going to construct an optical object function. So we're going to assume that this is sort of a phase object, and we're going to kind of construct its optical properties. We're going to compute the hologram we would expect to see on our CMOS sensor, simulate what we'd expect to see experimentally by removing the phase, adding some noise, downsampling, and then reconstructing, and then compare essentially the results of this model and this simulation with what we see experimentally. So I'm going to go through each one of these steps in kind of a little bit of detail. So the first detail is to kind of model the family of the shapes of these lenses. And the equation we're using to do this is the Young-Laplace equation. This is the same equation that models the shapes of soap film, soap bubbles. It essentially relates surface tension to curvature and to pressure. So in this case, this surface tension is this gamma. This is a pressure drop, which is kind of the pressure difference between whatever's inside this little liquid bubble or liquid droplet versus the outside. And then this is the curvature of the interface. If you expand this curvature, you get this type of equation. So this ends up being a nonlinear second-order ODE. So there are two derivatives, and things are buried inside square roots and powers to the 3/2. So the way we've been solving this is we've been solving this numerically, and it requires two boundary conditions since it's a second-order ODE. And those two boundary conditions for this isolated lens case are contact angles. And the reason why we're choosing contact angles are these are material properties. So contact angle of a liquid hitting a material doesn't really depend on the geometry. It only really depends on the materials involved. This, at nanoscale, that begins to become a little bit more fuzzy, and there may be some questions. But for the purposes of this model, as long as you're kind of above a few tens of nanometers, this seems to hold fairly well. So we're going to use these boundary conditions, and then given these boundary conditions and given this ODE, we can then reconstruct what the shapes of these particles would be. And the reason why we get a lot of different solutions is we don't necessarily know what this delta P is. This is essentially a parameter, and this corresponds to the size of the lens as it's growing in time. So on the other side of things, we can look at these continuous film nanolenses. The equation we're using is pretty similar. So again, it's this Young-Laplace equation. We're adding in another term here, and this is a disjoining pressure. So this becomes important when you have very thin films. So you notice this H is at the thickness of the film. When this H gets around the 10 nanometer level, this term kind of starts to become significant. So really, everything on this side is you're adding up different force terms. And so it's okay to add different force terms if those terms are significant. So you have to make sure you're capturing everything that's significant. And in this case, our boundary conditions, again, we have two boundary conditions. They're slightly different. One is still the contact angle on the sphere, and the other boundary condition is this film thickness at infinity, because there's no contact between this film and the substrate at a specific point. So these two types of lenses are nucleation-driven. You can think of this as being small droplets and film-wise condensation. So the second step is once we have this family of lens shapes is how quickly are these lenses going to build up over time. And we can also answer this using essentially fairly simple gas dynamics. So this is the Maxwell-Boltzmann distribution for how quickly are molecules in the vapor phase just hitting a target, hitting an area. And so as those molecules hit an area, they kind of add to this film as they condense, and this builds up over time. So this gives us this dependence in time. For the isolated lenses, we still have that same sort of dependence in time at late times, but initially there's a nucleation event that has to happen. So it's a little bit more complicated, and I don't really have time to get too much into the detail, but there's another term that is how quickly do we first start to form this lens, and then once it's been formed, how quickly does it kind of take off and grow. So it turns out that, as I said, I don't have time to go into all these details, but it turns out that for the parameters I've shown you so far, these continuous films really fit the best, and I'll show you how well they fit our experimental data. But we have used that other model, that isolated film model, in a couple other experiments. One was looking at especially that tilting-based formation that I showed you, where these little droplets get trapped in the wake. And then another was actually using, in this case, vapor condensed droplets as little micro-reflectors in fluorescence microscopy. So there are a couple applications where that has been interesting. But anyway, so to summarize what the conclusions were from this nanofluidic modeling, we have our family of shapes, we have how quickly they're growing, and we're going to assume this continuous film lens approach. And so the next step is to send these results into an optical modeling scheme. And so to illustrate this scheme, I'm going to show you two cases. One case is we're looking at a 50 nanometer diameter particle without any of this film around it. And then in the other case, we're looking at a 50 nanometer diameter particle with this film around it. So here we're plotting the phase of this object. And so if there's this film has some thickness and some refractive index. And so as light goes through it, it accumulates some sort of phase. And so you see that there's this kind of grayscale background that's tapering off. And that's the effect of this phase object, where in this case you don't see that background. So the next step is we can compute what type of hologram we'd expect to see. So in reality, both of these would generate a hologram. In this case, you can't really see it, and that's because I'm plotting both of these on the same scale. You'd need to go to about the 5th decimal place in terms of these variations, and then you'd start to see this hologram down here. The next step is we're going to simulate what we might see experimentally by adding some noise to this hologram, and we're going to make sure that we don't have the phase information. And we're going to then downsample it to the pixel size of our sensor. So in this case, pretty much everything you see is noise. Here, mostly what you see is noise. But if you look closely, you might be able to see some remnants of some sort of circular pattern there. Once you simulate the reconstruction procedure, it actually becomes much clearer, and you can actually kind of see a very clear, strong signal, in this case from this 50 nanometer particle, whereas here you don't see any strong signal, you just see noise. And so this model, so this is kind of a long, involved model that went into this. We started out with that nanofluidic modeling part, and then we sent it to this optical model, but it fairly accurately replicates the detection of 50 nanometer particles under 1% Gaussian noise. So what we can do is we can take this model, and we're going to apply, in this case, one fitting parameter to try and fit this to our data. And this fitting parameter is the density of molecules in the vapor. So it's how many PEG molecules are there floating around and hitting our substrate. So we use this as one fitting parameter, and then we can see that this fits reasonably well. And so in this case, we're showing the prediction from the theory, and then this would be the prediction for the beads without any nanolenses, without any PEG. So as one sanity check, what we can do is we can compare this to Rayleigh scattering. Because you can think of the idea of being able to detect very small particles as very similar to Rayleigh scattering. So Rayleigh scattering is the reason why the sky is blue. It's why small particles scatter light. And this is the typical sort of equation that you would get for the intensity of that scattered light. So there are a lot of different dependencies here. What I'm going to highlight here is the dependence on particle diameter. So typically Rayleigh scattering scales with particle diameter to the sixth. In our case, we aren't measuring really directly the intensity of the scattered wave, but we're measuring how the scattered wave interferes with a reference wave, because we're doing this holography. And so our scaling isn't going to be proportional to the scattered signal squared, but it's really just the amplitude of the scattered signal. And so that's going to give us a d cubed scaling. And so if we compare our model, what that predicts without nanolenses, we get this d to the third scaling. And so as a sanity check, the kind of long-developed model here makes sense in terms of, at least from the optical standpoint, in terms of what we're detecting. One interesting thing to note is that once we add the nanolens, the scaling is a little bit different. It's no longer this d to the cubed, and we've actually kind of pulled this curve. You can kind of think that as this scaling relaxes, this angle kind of comes up. So one thing I guess I should have mentioned is this is being plotted on a log-log plot. So any of these sort of scaling parameters end up as lines. So this d cubed is the slope of this line. On that case, the 1.6 is the slope of this line on a log-log plot. And so by being able to pull this line up over here, by reducing its slope, we can actually image these small particles above our detection threshold. So these two lines, again, this lower line here is about the noise level of our image sensor, and this is then 3 times the noise level, which is what we're using as our practical detection threshold. So not only can we detect spherical particles, we can also detect different shapes of particles. So this is looking at carbon nanotubes. So these are, as far as carbon nanotubes go, these are fairly thick. They're 90 to 100 nanometers in width. And you can see that before condensation, we can't really detect them. But after we condense these nanolenses, we get strong signals. Another interesting thing to note is that these carbon nanotubes are very hydrophobic. So you wouldn't normally be able to kind of immerse them in a solvent. But yet, this procedure is still working fairly well, and we're still getting these nanolenses condensing around these objects. This is an example of looking at carbon nanotubes again, but these ones are much thinner. They're sub 20 nanometers. And this is an example that's really right at our limit. So these are things that are kind of, it's beginning to become a bit questionable. If you look at it, is this really an object? Is it a spot of noise? But I don't know. If you have a little bit of belief, you might be able to see an object. But this kind of gives you the, the limit of where we are in terms of that size. So what we can do is we can take these results, we can add them to our graph. We aren't adding any new fitting parameters. We now have results from 3 different kind of sets of experimental data. There's the spherical particles, there's the carbon nanotubes with the nanolenses, and then there's the carbon nanotubes without the nanolenses. And considering that we aren't really adding any new fitting parameters, things still fit reasonably well. So the last thing, so I think I've shown you so far that I've given you a demonstration of this imaging system we've used. I've shown you that we can go down to things as small as about this 40 nanometer here. So we can boost our sensitivity to be able to detect these very small particles, very small objects. So I'm going to show you a couple other areas here, in particular how we can have some level of specificity, how we can achieve some portability using these types of devices, and then how we can do robust quantitative sizing. So the first thing I'm going to show is specificity, and many applications require extracting a single type of particle from a heterogeneous sample. And nanolenses formed via condensation are compatible with functional surface chemistry, and we're going to use biotin and streptavidin as a model system. So biotin and streptavidin are two molecules. This is a small molecule. This is a protein. And these 2 molecules happen to bind very strongly together. And it's kind of a very typical initial system that people will use when they look at binding. So in this case, what we have is we have a cover slip that we're coating with biotin molecules in this case, and we're going to look at 2 different types of particles. So these are just beads. They're red fluorescent beads and they're green fluorescent beads. The red ones are just plain beads. The green ones happen to be coated with streptavidin, and the size is both about 100 nanometers, so the size is the same. So in this proof of concept experiment, what we're going to want to do is we're going to want to preferentially capture the green beads and hopefully reject the red beads because we want to get some level of specificity. So this is what the sample would look like if we didn't use any functionalization, if we just took our solution and kind of dropped it on the surface and let it evaporate. You see there are many, many red beads. There are a few green beads buried in the background, but there are a lot of red beads. If you do functionalization and then you do a little bit of washing so that you can specifically capture these streptavidin beads and wash away the red beads, you'll see that we're able to capture specifically the green beads. So these images are just conventional fluorescence microscope images. So then the next step is we want to make sure that we can, with this surface functionalization, we can still see them in our lens-free holographic imaging system. And so what we do is we start with this fluorescent image. We then do our nanolenses via condensation. We take them and we image them in our lens-free imaging device. And what you'll see is there's pretty good agreement. In some cases, there are a few small dust particles that don't happen to be fluorescent that we also see. But in general, we get pretty good specificity between these green beads and red beads. And we use SEM to make sure that some of these spots really do correspond to individual beads because these beads sometimes have a tendency to aggregate. So we can still see single nanoparticles, and we have some level of specificity here. So that's one advantage of this technique. Another thing that we can do is we can actually move this toward a field-portable and cost-effective implementation. And in this case, we're integrating the nanolens formation and the imaging inside the same device. This would be suitable for particle sizing applications in low-resource areas. You can compare it to other sorts of technologies like dynamic light scattering, nanoparticle tracking analysis, and electron microscopy if you're only using the microscopy to do particle sizing. Of course, electron microscopy gives you a lot of other advantages in other areas, but if all you care about is particle sizing, then this would be a competitive technique. And then the other advantage is that you can visualize the film deposition in situ. So what we have here is we have our CMOS image sensor facing downwards. We have our sample also facing downwards. We have a pool of this liquid polyethylene glycol heated using a small resistive heater. And so some of this is going to then evaporate, and then it's going to condense on our sample. And then we have our light source imaging system down here. And we have multiple LEDs so that we can shift the image using that pixel super resolution approach, so we can provide small little shifts to the image. So one advantage is that we can get time-resolved measurements. So we can actually record the formation of this film as a function of time. So this is looking at a single 83 nanometer bead, and we're recording the signal as a function of time. And the black dots are what we measure experimentally. The red curve is the simulation prediction, the same sort of simulation I showed you before. We again have one fitting parameter, which is the number of molecules in the vapor. And essentially this curve comes from computing the shapes of these nanolens profiles over time. So over time, we can say there shouldn't be any nanolens at time 0. At time 350, it looks like this, and then it slowly builds up over time. The reason why there's some sort of peak here is because at late times, you're kind of burying your particle under a layer of snow, and if there's too much PEG, then it hurts you. And so there's an optimal nanolens shape, and the fact that we can visualize in situ allows us to kind of capture this optical nanolens shape regardless of the vapor density. So if we had a higher vapor density, what would happen is these dynamics would just happen faster. So we'd kind of squish this curve to the left, but this peak value wouldn't change. So this peak value doesn't depend on the vapor density. It's only the time at which this peak value occurs. And so this is going to give us the best sensitivity to small particles, and it's also going to give us a potential for quantitative sizing even when the vapor density is unknown. So here what we're going to do is we're going to kind of take this graph, and we're going to pull out this peak value, and we're going to do this for a lot of different particles. So there's about 120 different particles, and we're going to plot the value of that peak phase as a function of particle diameter. And you can see that they agree fairly well with this red physical simulation prediction. And so now, in this case, we've removed all of the fitting parameters, because as I said, that peak value doesn't depend on that fitting parameter. And so we get very good agreement considering that we have this experimental data, and we're fitting, and there's a model that fits it very well without a fitting parameter. So this is pretty much what I said. So this is from 5 different experiments, about 25 beads per experiment. Physical simulation prediction fits extremely well, so we have a good understanding of the physics behind the simulation. If we want to use this as a practical sizing tool, we can actually apply a calibration curve. And so in this case, we're doing an empirical fit. And the reason why we're doing an empirical fit is this physical simulation prediction seems to break down a little bit. It seems to be not so good at the very large size scale. And so if we want to kind of capture particles over this whole size scale, what we can do is we can just do a second order fit. So you can imagine this being a kind of a second order polynomial fit. And then what we can do is we can compute the root mean squared error of our experimental data compared to this fit. And we get an RMS error of about 11 nanometers. And so this provides our sizing accuracy. In this case is between 40 nanometers and 500 nanometers, is about plus or minus 11 nanometers. So then what we can do is we can take this calibration curve and we can apply it to other unknown samples. we know sort of what we're putting in here, but we don't know the exact sizes of the particles. And so we can kind of look at histograms and make sure they make sense. So in this case, this is 50 nanometer nanobeads, and we see a peak around 50 nanometers. This is looking at 100 nanometer beads, but one interesting thing here is this is a very dense amount. So there are more than 30,000 beads within our field of view, but yet we can identify each one individually. And they happen to be so close that sometimes we're picking up clusters. But you can see we can we're getting this peak at 100 nanometers, and we can image a very large number of particles. Another example is looking at two different sizes. So this is a heterogeneous mixture of 100 nanometer particles, 250 nanometer. This is a mixture of 4 different sizes. One of the technologies this might compare to is something called dynamic light scattering, which I can maybe talk about more in detail if you have questions. But dynamic light scattering has a hard time doing these very inhomogeneous particle mixtures. So if you just have one Gaussian peak, it does a pretty good job. If you have 2, you can maybe do it if you play some tricks. But once you have a lot of peaks, it becomes hard to size and get a quantitative distribution. But here, since we're measuring each particle individually, we can get a very large number of different sizes. One of our collaborators was interested in making these bowl-shaped nanomaterials. So what these are, they're small silica kind of bowl-shaped. He called them nanocrescents. But inside, there's a small layer of magnetic material. It's gadolinium. And this magnetic material, so the idea is to use these as MRI contrast agents. But he was interested in what were the sizes he was making them. Were they fairly narrowly distributed in size? And he initially tried dynamic light scattering, but it didn't work very well for his application. So he was using TEM, so transmission electron microscopy, which is, of course, very expensive and pretty slow and pretty time-consuming. And if you qualitatively compare the results we get with a TEM histogram, they look pretty good. Ours are shifted a little bit to the left, and that's because we're using this calibration curve that was developed for spherical particles with these kind of bowl-shaped particles. What we could do is we could go back and develop our own calibration curve for these bowl-shaped particles, and then this would shift back over. So really what we're measuring is we're measuring some sort of effective diameter, probably based on the volume of this or based on the height, something like that. But it worked pretty well, and he was pretty happy with those results. And then this is an example of looking at a biological sample. So this is an adenovirus. So these should be 60 to 70 nanometers, and we're getting a peak at about the right place there, too. So we can size heterogeneous samples that are mixtures of different sorts of things. We have a large dynamic range in terms of concentration, so we can go from just a few particles up to tens of thousands, and we could probably push this a little bit more. So 10 to the 5 orders of magnitude range in concentration. We can handle non-spherical particles, although you might need to do a little bit of a change in calibration. And we have a large dynamic range in particle size. Since this is essentially an imaging approach, we can go all the way down from about 40 to 50 nanometers up to whatever you could fit on your imaging sensor. So I should say that if you have large particles, things larger than a micron, you don't have to do this nanolens self-assembly. You can just image them directly, but you could use the same sort of device. So we also have, one of the things that went into generating those histograms is this kind of automated particle identification procedure. And so I just wanted to mention it quickly, where we can identify individual particles. And the way we actually do this is we count the large particles first, and then we remove them, and we remove their associated twin image noise, which are these concentric rings around it. And this allows us to actually detect small particles and make sure that we're detecting real particles and not just kind of some of these rings around the larger particles. So with that, I can conclude, and I want to again highlight the main advantages of this technique. So we're sensitive to particles as small as 40 nanometers. We have quantitative and automated sizing. We can do this with very high throughput because we can image over a very large field of view. It's portable and low cost, label-free, rapid, a potential for specificity. And then again, this kind of falls under this larger umbrella of my interests. And going forward, there are some research projects that still deal with this, but I'm wanting to kind of expand a lot, but still stay within the soft nanophotonic systems, and probably especially with kind of a focus on fabrication and biosensing and bioimaging. So if you have any questions, I would be happy to take them. Thank you.